In this video, we're going to work a couple of example problems where we estimate the size of the remainder of a partial sum based on series that we tested for their convergence using a comparison test. And so remember, the idea is, this series here for this first problem, it looks like you could apply the integral test to this. Well, what I've mentioned in previous videos is that if you would rather estimate the size of this remainder using the integral remainder test than the comparison test. That would be more accurate, but these problems are just to, a lot of these problems are just so we can practice these tests for convergence. So just imagine that the only test that we could use to figure out the convergence of this series was the comparison test. So we can only estimate the remainder using remainder estimates corresponding to comparison tests. Okay, so let's go ahead and we would test this for convergence first, right? Just like imagine that this might be a series that we could actually maybe get the S sub n, or again we could test this for convergence using another method other than comparison test. Imagine that we can't find the S sub n of this, and we only can use the comparison test to verify its convergence. So what we do is we say that we bring in a comparison series, and so we can see here that if we say we bring in b sub n as 1 over n to the 5th, we want to do this because we understand that this is a p series with p is greater than 1, so we understand how this series behaves. We know its convergence with the integral from the integral test, and we can estimate the size of its remainder as a series. If you put this b sub n into a series using the integral test for the integral remainder theorem, okay? But then we also bring this in because this is always greater than or less than to the terms of going from 1 to infinity of the series we're studying. And so what is it? Greater than or less than? Well, it's always greater than, because the denominator is always smaller for every single n. Okay, so now, but still, is this one of the cases where we get information? Well, okay, this is convergent. This p is greater than 1. This is convergent. This is always greater than this. So that, yes, that means our series is convergent. Okay. Now, remember that when it comes to these estimating the sizes of remainders, only applies if you have a convergent series, right? That's what it's all about. You found out that the series is convergent, so now there's an infinite sum, S. If there's not an infinite sum that's equal to S, like it's convergent, so we can say this equals to a value. That's the remainder theorem is based on this being equal to a value, this infinite sum. So it's equal to a value S. All right. Now, so remember, the idea is, imagine that we couldn't get an S sub n for this, an explicit S sub n. If we could, then we wouldn't be doing any of these convergence tests. We just test for convergence with the S sub n and get the value of the infinite sum with the S sub n, the actual explicit formula for the S sub n. But we can still write the S sub n as a sum. We can't get the formula for it, but we have the A sub n here. Right? And so the idea is we can still put this into a computer program and say like n is equal to 5,000 and get an estimation for S. But we'd like to know, if we can, how good is that estimation? That's what analyzing the R sub n is all about. And if you don't know what the R sub n is, I've talked about that in detail in previous videos. Go take a look at the previous videos. So I'm assuming you understand exactly what R sub n is. Okay, so what we're going to do is we're going to take the sum of the first 10 terms and then see how accurate that is. But this is just for practice. You can imagine in reality, you'd put this into a computer program and take the sum of the first 1,000 terms, 5,000 terms, right? But just for practice, we're going to do the sum of the first 10 terms. So we've got 1/5 plus, and then 2 to the 5th. Okay, so this is going to get pretty I just put this in. Let's just go straight to the calculator here. So, all right, we've got 1 over 5 plus n to the 5th. All right. Save that as the equation E. And so now what we want to do is we've got E with n is equal to 1. Yeah, so this would have been 1/6. We just start with 1/6. Okay, plus E plus there we go. Okay, so there we go. I'm not writing that out. 0.199263. So S of 10 is approximately equal to 0.199263. Okay, let me clear all this. All right, now how accurate is this estimation? All right, well, how do we estimate the size of an R sub n based on a series that we tested using a comparison test? Well, the idea is what we're going to do is, so for any comparison test, we brought in a B sub n for comparison. And the B sub n we brought in, we understand how that behaves as a series, or else we wouldn't have brought it in. Well, since we understand how it behaves as a series, then we in general, we're going to understand the size of that series is R sub n, right? We know, so we studied harmonics or P series using the integral test. So we also could get the size of the R sub n for any P series using the remainder estimate for the integral test. And so what we're going to do is we're going to compare that R sub n for the B sub n, which we're going to call T sub n, since we're going to call, this is going to be the R sub n that we're interested in. We're going to call this T sub n for these types of for comparison test remainder size estimates, so that we're going to compare this T sub n to this R sub n. And what happens is, because we're able to do it this way because a property of these comparison tests, the nature of them, and it's for the standard comparison test, this is the case, but for I think the limit comparison test, most if not all cases, this will be the case as well. But I guess it wasn't a requirement. But this is we're only talking about convergent cases, right? So for the standard comparison test, if you determine that the series you're interested in is convergent, what was the specifics of that? Well, in that case, the B sub n you brought in was convergent, and it was always, the terms were always greater than the terms of the series that's being studied, going from the entire range, or at least any point n to infinity. It was always greater than. And so since it was convergent and the series you're interested in is always less than, then it means it must also be convergent. Well, in that case, then because it's always less than or like that, then the T sub n bounds this R sub n from above. That's the idea. Now, when it came to the limit comparison tests, I don't think it was a requirement that the B sub n had to be like greater than the A sub n. In a lot of cases it was, because you went from the general comparison test to the limit comparison test, like with a B sub n that was always greater than the A sub n. Okay, but if if for some reason you used the limit comparison test and you didn't have a b sub n that was always greater than the a sub n, then then you couldn't use this method. But I think for the vast majority of the problems that you use any comparison test, limit or standard comparison test, it's the case for the convergence case that the b sub n you brought in that's convergent is always greater, the term's always greater than the a sub n terms, going from any point, some point to infinity. And so that's the idea. We're calling this the t sub n bounds this r sub n above. So you use this t sub n to make a statement about this r sub n. And so, okay, in this case, again, we can, the information we know about this particular r sub n, or this particular sequence here, is based on the integral test, right? That's when we studied p series with the integral test. So let's get this, we're going to call this a t sub n using the remainder estimate for the integral test. And so there's a couple of ways of looking at this. So you could say this, okay? The r sub n of this is going to definitely be less than this, for sure. Okay, so we could start by saying, let's go from n is equal to 10 in this case to infinity. Let's take this integral with n is equal to 10. So, okay. And then we replace the n with an x. So we've got the limit okay, so the integral of x to the minus 5, x to the, okay, minus 5 plus 1 is minus 4. So x to the minus 4 over minus 4. So bring out the minus 1/4. Okay. 1 over t to the 4th, evaluated from 10 to 1 over x to the 4th. Evaluated from 10 to t. Okay. So we've got 1 over t to the 4th minus 1 over 10 to the 4th. 10,000. So as t approaches infinity, this goes to 0. You have minus 1 over 10,000 times minus 1 over 4. So 1 over 40,000. Okay, so you could stop here and say that the r sub 10 here. So again, we have t sub 10 is always less than or equal to, and so what is 1 over 40,000? So okay, now since we know that this bounds this above, then r sub 10 is less than or equal to that value. Okay, and now I was thinking that we could, if we wanted to, we could take this a step further. And so if you remember when we did the integral test remainder problems, we could get actually a more accurate estimation for the remainder for this by we get the lower bound. So we have a lower bound on t sub 10, and then we will get the actual, we would get the sum here, the s sub 10 here, and then you add that s sub 10 to all sides of the inequality, and you have a bound on the infinite sum, and then you could use that to improve the remainder estimate, and I was thinking we could kind of extend that improved t estimate here, and that would be an upper bound on this r. But I don't think, actually, looking at this more closely, I don't think we can do that. And I might have, when we went through the textbook section, I might have mentioned that we could potentially do that, and it doesn't look like we can. So for a comparison test, at least for the case of if the b sub n you've brought in, you're getting that remainder using the remainder estimate for the integral test, I don't think you can go that extra step of like improving the remainder estimate. I think you're done here. Once you get the upper limit on t, then that's the upper limit on the r. Because even, like, you might say, well, can we use the lower limit? Well, no, because you don't know that lower limit. You don't know how that lower limit relates. Like, we didn't make a statement about how much less, like, for each term, how much less is each of these terms than the b sub n terms, going from 1 to infinity. We didn't make a statement about that. We just said for sure they're less. So we can't make any, we can't go that extra step. We can't use that lower bound. We don't know how that lower bound relates here. We just know for sure that this upper bound must be greater than the remainder for this series. That's the only statement we could make here. So again, I might have mentioned in that when we went through the textbook that we could use this r sub n here, what we're calling t sub n, and then get that as an upper bound, and then go a step further and improve on that, like we did for just the general integral test remainder. But we can't do that here. Okay, so this is it. But still, though, this is a very good result. What we know is that, and we still might be able to improve the estimate here. So, okay, the infinite sum s is equal to s sub 10 plus r sub 10. This is exactly equal. This is an exact equality here. If you don't know what this means, go back and watch the previous videos. But so you say, okay, well, there you go. Add S10 to R10, we'll get the sum. Well, no, we don't know what R10 is. We have an idea of its size. That's the thing. We don't know exactly what R10 is. We know it's less than or equal to 0.0025. But we also know that it's greater than 0.199263 at the infinite sum s, right? For sure. It's definitely greater than this. So we know that s is less than or equal to, okay, well, s is greater than or equal to 0.199263. And then we know for sure that s is less than, because we know the upper bound on r sub 10. .199288. We know for sure that the infinite sum is less than or equal to this. And so actually we could say, technically, we know it's greater than this. We know it's not equal to this. It's definitely greater than this, but it could be this, or it could be something less than this. And so, okay, why don't we just take the midpoint of this, right? Because the point of putting 10 in here was we're trying to estimate the infinite sum. If we had the infinite sum, then we just go ahead and use that. So that's the purpose. So we can replace this, well, we'll call it S10 prime, because it's like an improvement, right? It's still associated with S of 10, but it's like an improvement. So minus 0.199263 divided by 2 plus 0.199263. 0.199276. So this is a better estimate of the infinite sum. And actually, yeah, we have improved the r sub 10. We'll call it r sub 10 prime. What's this going to be? It's this range here. 0.199288 minus 0.199263. Okay, yeah, right. We haven't changed the range. Okay, so we did improve the r sub 10. Oh, no, we have, because we divide this by 2. That's right, we have improved it, because we can divide, exactly, we divide this by 2. Yeah, so there we go. So you can improve the estimate. Cool. Okay, let's work another problem. And I wanted to do another problem because the B sub n is not going to be something that we understand based on the integral test. So I thought it'd be good to look at comparison remainder estimates from another angle. So okay, here let's use the comparison test. We've got, let's say we remove this cosine squared of n. So we get 1 over 5 to the n, which is 1/5 to the n power. That's a geometric, if we put that into a series, it's a geometric series with the common ratio absolute value less than 1. So this is convergent. All right, now how does that relate to this? Okay, well, so cosine squared is always going to be between 0 and 1. Now, with the integers, we could actually constrain that further because, like, pi, 2 pi, 3 pi, 4 pi, 5 pi is never 0. That's never an integer, right? So actually, you would, since cosine of n is 0 or 1 at some value of pi, some multiple of pi, cosine of n is 0, 1, or -1 at some multiple of pi. But we're never going to have, with the n, we're never going to have a multiple of pi with the integers. So you can think about it that, and so, but since it's squared, we're never going to be between 0 and -1. But you can think about cosine squared of n, the integer n, is going to be less than 1 or greater than 0, not equal to. If this was, if it was cosine squared of x, this would be equal to. But with the n, it's always in between, somewhere in between 0 and 1. And so with that, you can see that this is always going to be less than, right? Because this will always be less than 1, and you've got 1 over 5 to the n. Okay, so this is convergent. This is always greater than this from 1 to infinity. So that means this is convergent based on the comparison test. Okay, so our B sub n this time is a geometric, it corresponds to a geometric series. And how do we know that this is convergent? Did we use the integral test? What do we know about this? Well, we actually know a lot about geometric series. We could get the literal S sub n formula for this, and we could also get the actual infinite sum of this. We couldn't get the actual infinite sum or the formula for the P series, but this we can. Okay, so same process. Let's go ahead and we've got this. So this S sub n here is okay. So what is S sub 10? So we've got cosine of n squared divided by 5 to the n okay. So E with n is equal to 1 plus E with n is equal to 2. Let's see, n is equal to 3. Oh, damn it, I deleted the... Damn it, I deleted the... Okay. Okay, so 0.073929. All right. So now, what's the R sub 10? Like, how big is the R sub 10 for this? So, okay, with the geometric series here, we were able to use mathematical techniques to determine the actual S sub n. Like, not a summation. So this was the first term. So what's the first term here? B sub 1 is 1/5. Okay, R is equal to 1/5. So S sub n, we might not need S sub n, is the first term times 1 minus R to the n over 1 minus R. And then the infinite sum S, okay, wait, let's put a T up here, because I don't want to confuse this with the main S's in the main variables. All right. The infinite sum of a convergent geometric series is the first term over 1 minus the common ratio. Okay? And so the idea is, again, when it comes to comparison tests, estimations of R sub n, it just depends on the B sub n you bring in. You're going to use whatever you know about the B sub n, whatever you know about its remainder, and the fact that it bounds, it's always greater than your main sequence, your main series, to create an upper bound on the main R sub n. Okay, so what do we do here? Well, what we can do is we can plug in n is equal to t here, get S sub 10 to the t, and then subtract this from this with n is equal to 10, and we'll get R sub n t. And that will be the upper bound on this. So the difference is we're going to get an exact value for the R sub 10 for this series. That's the difference. With the integral test in the previous problem, that integral test gave us an upper bound on the B sub n series. Here we're going to get the exact R sub n. And we know that this is going to be definitely less than or equal to that. So, okay. We've got, so this is 5 over 5 minus 1 over 5 is 4 over 5. So 1 over 5 times 5 over 4 is 1 over 4. So there's the infinite sum. Now, this is, so 1/5 minus 1 minus, and then we have 1 over 5 to the 10th, and then this is 4 over 5. 1 over 5 divided by 4 over 5 is 1 over 4. So, okay. 5 to the 10th is going to be really big. 1 divided by that is that. 1 minus that times 1/4. Okay, so this is approximately equal to what? 0.25. And why is that? Because this is so tiny. 1 minus this tiny number is pretty much 1. So, and actually, so we actually need to come back here. This is because if we subtract these two, we get 0 for the R sub n. So the R sub n is going to be very small. So let's actually take this, and so let's take this off, and let's subtract 1/4 from this. And there you go. There's R sub n. 2.56 times 10 to the minus 8. Well, no, that's T sub 10 for this geometric series is equal to 2.56 times 10 to the minus 8. And therefore, this r sub 10 is less than or equal to 2.56 times 10 to the minus 8. So that's how accurate this estimation is, and that's just 10 terms. Imagine we put in 1,000 terms into a computer program, you know. Now, I'm looking in the calculus book, and they're saying that this should be 6.4 times 10 to the minus 8, but looking into it, they did use the integral test on this. But to me, that's not what you would do. You would use the most accurate method you have for getting the remainder. And in fact, it said this in the textbook. I'm looking at the textbook right here. It says if b sub n, the sum of n is equal to 1 to infinity of b sub n is a geometric series, then t sub n is the sum of a geometric series, and we could sum it exactly. So the answer that the textbook gave was based on using this for the integral test. But why would you do that? You could get the exact t sub 10. We know that the exact remainder of this b sub n series is going to be less than the corresponding remainder for this for sure. So maybe I'm going crazy, but to me, this is the correct answer. Again, why would you use the integral test to get the remainder here? This is a geometric series. You know you could get the exact remainder. Why would you get an estimate? Why would you just get the exact remainder and use that as the upper bound on this remainder? So maybe I'm going crazy. If I'm missing something, please comment. Okay, but again, can we improve this? Yeah, we can. How? Because what we can do is we can say that, again, remember the whole purpose of this is not to get a partial sum. We would use we're trying to estimate the infinite sum. So what we know is that if we take the s sub 10, the infinite sum is going to definitely be greater than this. Right? For sure. But we also know it's going to be less than or equal to the s sub 10 plus the r sub 10. Right? We don't know exactly what the r sub 10 is. We know for the geometric series what it is, but not for this series. We don't know exactly what it is, but we know it's at least less than this. So 0.073929 plus this. And so, well, okay. 7.3929 E I mean, I don't know what my calculator's giving me trouble, but the idea would be you would get that upper value. I mean, this is still, I don't know why you would need this level of accuracy. I'm just trying to illustrate the concept here. This is really accurate, right? I don't know why you would need to go any further than this. But you would get an upper bound on S. Then you would replace your estimation with the midpoint between those two. And then your new R sub 10 would be this divided by 2. Again, you might say, well, who cares? It's already so accurate. This is just to illustrate the general concept. It's to raise your level of intuition on how these problems work. Okay, so there we go. There's remainder estimates for comparison test series.